All right, hello, my 101 students from Hazleton. It's Mr. Pashar here. I had some questions about the homework in the lecture notes, so I thought I should make some YouTube videos. So this will be a two-part series on section 5.1 from your textbook, which is prime and composite numbers, as I work here from my makeshift office until I get things up and running totally. Just as a reminder, please check Blackboard. So for Blackboard, I posted the lecture notes. You'll see homework number 5, which, by the way, is the correct one. In the email, I sent the old version of homework 5, which was from the old textbook from last few semesters, actually. So please check Blackboard. But I also did email you guys this morning the corrected textbook exercises to do. I hope everybody's healthy and well, and I'm here for you guys just to let you know that so we could finish this semester out and we could all pass this course and move on to bigger and better things, hopefully mathematically for some of you. But I'm always here. Any questions, please don't hesitate to call, text, or email. I'll do my best to get back to all of you as timely as I could. But I just want to go over some of the main things in this two-part series here. The main topic of this chapter really is number theory, and number theory is just a study of natural numbers. And you could spend semesters on this topic of number theory. There's so much we could do there, but we're only going to look at the tip of the iceberg. And in fact, most of the stuff that we're going to talk about, you actually have discussed, believe it or not, in elementary, middle school, but we're going to put more of an adult spin on it, of course, with some of the notations. The nice thing about working with this whole chapter is we deal with this nice set of numbers, which is just the natural numbers. So that's your counting numbers, 1, 2, 3, and so on. We don't have to worry about decimals, fractions, irrational numbers. We don't have to work with imaginary numbers, none of that stuff, just the nice natural numbers. So we're first seeing with this topic of divisibility, and most of you know what divisibility is. You know, if I say, what's 25 divided by 5? On a normal day, it's 5. You should know that. But we're going to actually look at where this idea comes from, and it's from multiplication. So if we assume A and B are natural numbers, we say that a number B divides a number A. If this thing happens, there exists a natural number K such that A equals B times K. In other words, division is really multiplication in disguise, and here's how it is. A equals BK. If we divide both sides by B, we get K equals A over B. So there's your division component as you normally would think of it. It comes from multiplication. So here's some examples for you other than in your lecture notes. 7 would divide 56 because 56 equals 7 times some number K. And as long as that some number K is a natural number, then it's divisible. And as we know, 7 times 8 is 56. So that means 7 divides 56, so that's good. On the contrary, 7 does not divide 51, so we put the slash through that bar, because that some number K that we would have to give us 51 would have to be 51 over 7, and 51 over 7 is certainly not a natural number, so 7 does not divide 51. So hopefully you understand that idea. That's not too rough. The next thing that you may see is this as an example in your text. They'll say find the natural number factors of a number, and we'll do an easy example here, 36. So oftentimes students say, well, where the hell do I go to think about what numbers are factors? Well, think of your times tables. Think of numbers that multiply to 36. So always start with 1. So 1 times what gives you 36? Well, clearly that's 36. This is an even number, and if you read the text or have known this through the years, any kind of even number is divisible by 2. So 2 would be a factor. 2 times what gives you 36? That would be 18. 18 plus 18 is 36. What's another factor? Well, let's try 3. Does 3 divide into 36? It does, 12 times. So 12 and 3 are factors. We also have 4 and 9, and 6 times 6. So these would be all your natural number factors of 36. Now in the next section, we're going to kind of up the ante on what this means in terms of what we call proper divisors, but we'll cross that bridge when we get there. So that's how you do such a problem like this in a textbook. That brings us to this topic here, prime and composite numbers. So the textbook gives you, big definitions. A prime number is a number that only has 1 in itself as factors. So those would be numbers like 3, 5, 7. Not 9 though, because we think sometimes that odd numbers are always going to be prime, but that's not the case. 11. And then one number that we sometimes miss is 2. 2 is a prime number because it only has 1 in itself as factors. So a composite number then is any number that's not prime, and these are the numbers that have more than 1 in itself as factors. So take 4, because that's 2 times 2, and that's also 4 times 1. A number like 9, because that's 3 times 3 or 9 times 1. Numbers like 8, that's 4 times 2 or 8 times 1. And then the list goes on and on. But a number that is neither prime nor composite is the number 1. 1 is neither prime nor composite, and you'll see that in definitions. That's important to understand. That's neither prime nor composite. I think I'll be able to get this all in one video for everybody. The last major topic here really is the fundamental theorem of arithmetic. Now, most branches of math have what we call these fundamental theorems. Calculus has one, algebra has one, and arithmetic has it. And what this theorem says is the following, essentially. Each natural number can be written as a unique product of prime numbers, as long as we disregard the order. For example, 2 times 3 is the same as 3 times 2, even though we don't switch the order. So what the heck does this exactly mean for just the lay non-math person? It just means no matter what natural number you have, you pick it. We could write that as a unique product of prime numbers in a way that no other number can share it. So think of it as each natural number has its own unique barcode. For example, let's take the number, let's see what I have here. Let's take the number 900. So what we do to figure out what this unique product of prime number is we look for what we call the prime factorization. And the prime factorization essentially says, take this number and make a factor tree out of it, and we'll figure out what it is. So your first step, obviously, what 2 numbers multiply to give you 900? And there's a lot of combinations of those numbers, but to me what comes to mind is 100 times 9. And then what we want to do here is break down each of these numbers until they're prime. So 100 is not prime. I'm going to write that as 10 times 10 because that's how I see it. Now, you may also write that as 50 times 2, which is fine as well. And there's other ways to do it too. 10 is 5 times 2. And now these are all prime numbers, so what I'm going to do is circle them. And we're done on that part of the tree. And now we're going to look at 9 because 9 is not prime. That is 3 times 3. And now these guys are prime. So the prime factorization is essentially just the way of writing this unique representation. So I'm just going to write out all the numbers I have first. So I have 5 times 5 times 2 times 2 times 3 times 3. There's your unique product of prime numbers. What we generally do is write them in terms of exponents. So that's going to be 5 squared because you have 2 of these, times 2 squared because you have 2 2's, times 3 squared because you have 2 3's. And that is the prime factorization of the number 900. So this is a direct application of the fundamental theorem of arithmetic. I hope this has helped you guys to do your homework for section 5.1. In the future I will post more of these videos. I hope everybody is understanding the material. Again, feel free to call, text, email me for any other questions. And I'm looking forward to the next section, which will be 5.3 and 5.4. So enjoy the rest of your day, and hopefully we'll see everybody soon at some point in time.